Alright, so welcome to my video on how to do the fifth question from the refraction worksheet. This is a question, it's actually a proof. So we're trying to prove that if we have some incident ray heading towards an unknown material, it could be any material, that when it strikes the material, it will refract, go through the material, and then refract again as it exits the material. But if you were to compare the incident to the final refracted ray, um, they'll be parallel. Essentially, it may shift over a little bit, but that it will not have actually truly bent start to finish. So what we're going to need is a few things to do that. We need to establish how we're going to label stuff. First off, I'm going to call this theta 2, just because I have to have a midpoint. I don't want to use theta r. So generally, Snell's law is that the incident refractive index over the refracted index, I know, is the sine of the refracted angle over the sine of the incident angle. Now, for our purposes, we're going to start this one. I'm just going to put my equation up here so I've got it. We'll start with what's happening at this point here. So in our first refraction. So in this case, using Snell's law, we would have n1 over, we need to decide what we want to call this medium. We'll call it n2. So n1 over n2 is equal to the sine of theta 2, right, the refracted angle, over sine theta I. Decent enough. Okay. Now, the next step here is going to be to write out, well, first we actually have to do some geometry now. So we now know that this refracted angle is some angle, but we need, in order to do the second refraction, we need this angle here. So if we take a look at those two triangles that are created in this rectangle, that's a kind of a, look at it in a geometric way. It being a rectangle, I know that this top and bottom are the same length, and the side on the left and right are the same length. So if I talk about this angle, I could just as easily flip my page and have been talking about this angle. Nothing's changed in my triangle. Right? The one tick is on the bottom, the two ticks is on the left side. Flip it. One tick on the bottom, two ticks on the left side. It's the same triangle. So essentially, geometrically, you can prove that whatever this angle is, if it's, in our case, theta 2, this angle is also theta 2. So back in our diagram, I now know geometrically that that has to be theta 2. This is my first, and I've got my second. So my second refraction is going to look like this. My incident ray is n2, so n2 comes in, and nr comes out, the final refracted medium. And that's going to be equal to the sine of my refracted angle over sine of theta 2. So these are two separate statements. This statement's dealing with the second refraction. This statement here is dealing with the first refraction. What we need to now recognize is that my n1, my incident medium, and my refracted medium are both the same thing. So we could just call them n, but in this case it's even better. We know that they're air, so they're both 1. So when I rewrite both of these equations, call this equation 1, and call this equation 2. So now I'm going to rewrite them. So if I rewrite equation 1, I now have 1 over n2 is equal to sine of theta 2 over sine of theta I. And if I rewrite equation 2, I get n2 over 1 is equal to sine of theta r over, over my mistake, I just looked up and realized that this had to have been a 2, not an r. I apologize for that. Over sine of theta 2. So I got my two equations. Now, we have to kind of combine these. They're very similar, but they're not quite the same. So if I flip either one, inverse both sides, reciprocate both sides. So I'll just do the first one. So if I reciprocate this one, I get n2 over 1 is equal to sine of theta I over the sine of theta 2. Now I have two equations that both are equal to n2 over 1. So I'm going to combine these two. So I can say the sine of theta I incident over sine theta 2 is equal to n2 over 1. Hey, that's equal to sine of theta r over sine of theta 2. Well, I can kind of just forget about this middle section here. And if I just have this equation, let's rewrite that just to be neat. Sine of theta I over sine of theta 2, that middle material, is equal to the angle, the sine of the angle from by a refracted ray over the sine of the angle in that middle portion. Now, both of these numbers are over the exact same thing, sine of theta 2. So if I multiply both sides by sine of theta 2, they cancel. So all I'm left with now is sine of theta I is equal to the sine of theta r, and simply doing the sine inverse to both sides would remove my sine equations and allow me to finally state theta I is equal to theta r. And that would be the end of the proof as far as what's expected. Now, if you want to take a quick look at why that actually would prove that these lines are parallel, if we go back up here, if we were to cut out this middle box, if we were to cut this out and take this piece and just drag it in and overlap it, we would get something, I'll kind of leave that up there for reference, we'll get something that looks like this. Maybe I should draw it a little better. So, I'm going to do this on a coincidentally exactly the same piece, just so we can kind of work with that a little better. Here's my normal. Incident ray coming in at some angle, and some refracted ray going out at some angle. Now, if these angles are the same, then pretty much based on, again, geometry from grade 9, there's actually proofs that this has to be two parallel lines. Because what we're stating here is, let's almost drop this line completely off. If we just have our normal and a line, and the angle here and here are the same, theta r and theta I are the same, then what we have is two straight lines that intersect at a point. It's a mathematical proof. So I won't prove that, but it just realize that if we have this situation, two lines intersecting, we know that they're both perfectly straight lines when this is true. So by having both the angles the same, which we've shown theta I is equal to theta r, we can conclude this is the situation we have, meaning that this portion of the ray, the incident portion, and this portion of the ray, the refracted portion, have to together create a straight line. Therefore, parallel. Thank you for watching.